Hello friends, welcome to CEC Live Lectures. Dear friends, today in this session we are going to continue in our series on performance analysis of computing systems. Under this series we are going to discuss an important topic, and the topic of today's discussion is random variables and inequalities. And for the discussion of the topic we have with us in our studios Dr. Advitya Sinha. Dr. Advitya Sinha is Assistant Professor in Department of Computer Science, and she is teaching in one of the leading institutions of the country. Dr. Advitya Sinha has immense experience, immense knowledge, and we believe that we are going to get more and more knowledge on today's topic through her experiences. So let's welcome our guest, Dr. Advitya Sinha. Hello ma'am, welcome to the lecture.
Thank you very much. So on today's lecture, we'll mainly focus on what is randomness exactly and how it impacts and how it is used rather for evaluating the performance of any system. Okay, and also we'll take up certain inequalities into account. So broadly speaking, we are going to cover what random phenomena is. There are so many phenomena that's occurring in the nature, and all of these phenomena, if looked at an instantaneous viewpoint, you'll find that there is no pattern into it. Though into long run we can see have some patterns into it. So to understand this randomness, we'll take up some examples. Then random variables. What are the variables that are actually going to store what type of values, what would be the time domain, the space, etc. Then coming to the distributions that support these type of random variables. And obviously there are two types of such distributions that exhibit randomness. That's discrete and continuous, depending upon what type of domain it is. If the domain contains discrete values, it becomes a discrete domain. Otherwise, if it's a domain with infinite number of values, uncountable number of values, then it becomes a continuous domain. And the distributions that model this type of domain, it comes under continuous distributions. Then we'll also introduce what mathematical expectation is and how this expectancy measure can help to find out the average performance or the average values across a certain domain of values. Then we'll go through some inequalities, as inequalities and limit theorems are very important for performing some sort of approximations during derivations. So this will include Boole's inequality, the very famous set of binomial inequalities, the benchmark Markov inequality, and its derived version, that is Chebyshev inequality. Now, first of all, it's important to understand what is randomness exactly. So we can take up any example from the nature. Say for example, if we want to question that whether it will be raining tomorrow or not, or maybe the instant, maybe an hour after, whether it will rain or not, or what type of weather it will be, it becomes very difficult to perfectly determine the climate condition of the next instant. But if we are, say for example, looking into this context over a longer period of time, maybe a year span or something, then we'll know that there is a season. These all are like seasonal events, and rain will mostly, more likely, more probable to occur in the rainy season. Maybe somewhere during the summer season, as these 12 months they are categorized into the seasons, right? So what our specific requirement here is to understand what is randomness, to understand its pattern through a long run by performing some long run forecast methods, etc., so that we can have a prediction of what is going to happen in the future, right? Now, this method can be used for analyzing the computer systems, as we have certain parameters that impacts the performance of computer system. So given all those parameters, the implicit and explicit performance parameters, along with the decision variables, etc., we can at least make a prediction kind of thing that for how long this particular computer system is going to operate, what would be the functional lifetime of such a system given the constraints and capacities into account. So randomness is basically, if we are taking the individual event into consideration for a particular instant, say, so in this point of time, the outcome that we get, that will be totally uncertain. It cannot be predicted, right? Now, for such a instant, basically we call such an instant or such a occasion in which some kind of event is going to occur, we call such a experimental outcome process a trial. Now, a trial behavior, it cannot be determined in advance because this trial is closely linked with the instantaneous outcome of a particular experiment or a particular natural phenomena or something. Now, since the prediction becomes infeasible, so what we do, we try to gather more and more random sample points from these type of events. Now, once we have gathered all the values for say several instants of time, then we can apply the well-known prediction models and the algorithms, the methods that are available, so that we can go for revealing first like analyzing the randomness, and with the help of long run forecasts and prediction mechanisms, this type of randomness could be revealed gradually. Now, few instances if we take up. The first is natural phenomena that we just spoke of. Next could be population survey. We don't know what survey results will be in the next year, but obviously if we take a look for the last 10 years, we'll know that it's always increasing. And also if we minutely take a look of it or develop certain models, we can also find out the distribution function of by what factor or what degree this population is increasing, and maybe the trend could be like with some error analysis could be made near perfect. Then comes the stock market trends. So this is also a very important area these days, because there's so many market policies, etc. there that rely on these type of stock trends. So it becomes important again to analyze, to understand the underlying trend, the prediction of this trend that is there, so that better policies could be devised and more and more enhanced strategies could be implemented. So beyond all these, the randomness is there, and what our aim is to find this randomness, analyze it, and develop models and methods so as to find a better prediction out of the system. And a very recent topic that these days that's trending is evolution of cryptocurrencies. Even these type of currencies, there are so many cryptocurrencies these days, and you can see that they also follow different trends, and this trend, when seen at a particular instant of time, is unpredictable. It's uncertain that towards what whether it will be a hike or it will be a fall. But if we take up the same trend, if we try to analyze it over a period of time, we can see that there is a gradual increase, or there is some seasonal events are giving some kind of impact on this type of evolution of digital currencies, etc. And obviously, when we are speaking of all these prediction of randomness, etc., because probability is all about measuring and developing models and methods for finding out this randomness in different forms in our life. So this prediction is always coming up with some kind of errors, because of these prediction errors, our mathematical model that we develop, they cannot simulate the real world trends or features. That's why we also go for error analysis, so as to perform whatever deviations that are being identified during this type of prediction process. So in the figure you can see that it's a trend of global temperature. So it's tending towards increase over time, right? So this type of phenomena, which is random for a short duration of time or for the instantaneous moments, but looking over a longer period of time, there is a gradual trend that we can reveal. Now, continuing with the random phenomena, what are exactly the random experiments? Because there are so many phenomena, but from where these phenomena are coming, they are mainly a result of different random experiments that are being conducted maybe by the nature, or sometimes it could be there could be some human intervention, etc. So it could be some man-made models rather. So if we take up some few examples, very general ones, the first is like coin tossing. When we toss a coin, or say we are just about to toss a coin, we don't know whether the result will be a head or tail. But at least we know that beyond head and tail, there won't be any other possibilities. These are the two possible outcomes, right? So, and once the coin is tossed, after that only we can get to know what the result is. So this type of experiments produces a random event. Similarly, die rolling. Whenever you are playing some kind of game with dice and all, you can see that though we don't know what type of outcome is going to come, how many points will be there on the face coming upward, but we always know that there are 6 faces, so this is the sample space that we have, right? So when we are talking about experiments, we know some outcomes are attached with it, and along with the outcomes, there are also 2 more important things. That is the sample space. That is the list of all the possible values that are there in the system. And if we take up a subset of these values, then we can refer to it as an even space. We can say that what is the probability that a head will come up whenever I toss a coin. So this heads, coming up of the heads, not the tails, but the heads, this will become one such event. There could be so many events given the complexity of the experiment. Okay. So similarly for rolling of dice, you can see that if we have an event, say we want to know what is the probability that or what is the even space that only we come up with even numbers only. So we can find out that 2, 4 and 6 out of the sample space of 1 to 6, only these 3 are the numbers that match the event of having even numbers. Okay. So the event space, whenever the event space that we design, they come up with a single value, we call it an elementary event. Otherwise, we call it a compound event whenever we have outcomes spanning over large number of values, that is more than 1. Now, since we know what the random phenomena is, and this type of random phenomena is being generated by the random experiments, so now the outcome that is being produced, we have to store it somewhere. So why not have variables to store these outcomes? But these type of variables that can hold the value of the random processes or the random experiments, they had to be a little bit special than the normal variables that we have in our mathematical theory, right? Say we call x equal to 4. It means that x is a value, x is a variable that for a value is being assigned to it, right? But what happens with this type of random experiments, that when this type of experiments are being conducted regularly, iteratively, over longer period of time, then one more parameter comes into play, that is the time factor. So a variable that also keeps track of a time parameter, say for instance, as of now, then such a variable we will call as a random variable, a variable that not only holds a value, but also this value corresponds to a particular time. Now, time could be one parameter. As the complexity of randomness in the experiment increases, there could be more than one dimension. It could be time, or it could be some space, or it could be volume, or any other parameters that might be impacting that particular experiment. So not only the value of the variable is important, but the acting parameters onto that variable is also important. So which is why we cannot use normal variables in our random experiments, but to store the outcome of our random experiments, the random phenomena, we need random variables. Okay. So what are random variables? Explicitly, it's an arbitrary variable whose values are outcomes of some kind of random experiment. Could be coin tossing, or it could be selecting a card games, etc. And each of these variables, they are always associated with the sample space and the event space, as they are connected with a random experiment. So obviously, a random experiment, whenever it takes place, it will have a sample of values from this pool of samples, some of the events can take place, right? So whatever values the sample space will hold, a random variable is always going to take up those values. And what else? Each variable possesses probability of occurrence of the events. Obviously, because given a sample space, we know that how many different number of subsets are possible. So when we have so many number of subsets, that is the events out of a particular sample space, it means that we would very interested to know that what is the probability of these subsets to occur, or which of these events would be more probable or more likely to happen in the course of time. And when we are now speaking of all sort of probabilities and randomness, so obviously the distributions also become quite important. Why? Because in what manner, or rather in what pattern, these values or these probabilities are being distributed, how these events are rolling into a circle, or whether they are just like that, they are coming or they are following some pattern out of long run. So to understand all these things, we need to have a study on these type of distributions of how the values are coming up, how these events are being set up. So this could be discrete or continuous, depending upon what type of sample space we have. If the sample space is discrete, that is, say for example, when we are rolling dice, it means that we can only come up with 6 faces, and our sample space will have strictly 1, 2, 3, 4, 5 and 6, nothing else, right? So this is a discrete sample space. So whatever distributions we will take up to model such experiments, though this experiment sounds very familiar and a very simple one, but whenever we have experiments that have maybe a very large scale sample space, but the values are discrete, then we will go for discrete distributions. And whenever we have something like continuous sample space, like we want to measure the weight of a person, okay, in that sense, what happens, it depends upon how many decimal values we are taking after the decimal point, and then we will just end up into more continuous values. So we cannot just say that how many numbers are there between, discrete numbers are there between 0 and 1. We cannot say that 0.1, 0.2, 0.3, like that, 9 or 10 values. No, it's not like that. Because whenever we are entering the decimal world, it means that the space becomes infinite. You can go through to, like, precisely speaking, you can go to 0.000. It depends upon what precision and biasness you are taking into your experiment. In this figure, you can see that if we are considering, say for example, discrete sample space, then what's happening? The sample space has all the collection of values that are that could be there as outcome of a particular random experiment, and whenever some event happens, this occurrence of event, this gets mapped to the real line of values, and the function that helps to map this events from the sample space to the real line, we call it the distribution functions. Okay, and all the distribution functions, we are mainly trying to find out the probabilities of what the probability of occurrence is, maybe at a particular instant when we are taking up discrete distributions into consideration, or we would be interested to know what is the probability if some interval of time is given, if that particular experiment supports a continuous domain of sample space. Now, let's come to the random distributions. Now, distributions, as we know, that depending upon the nature of the sample space, could be discrete or continuous. So, starting with the discrete random variables and its distributions, these type of variables will always consider a finite set of countable values. Not only that the set is finite, but whatever the values are, they are all countable values. And whenever we try to find out the distribution of such events that rely on the discrete values from the sample space, it means that we are always trying to find out the probability mass function. Okay. Whenever we go for the continuous random variables means that the space is again has a continuity of values, there is no discrete thing. So, at that point of time we will call this probability this function as probability density function. So, as of now when we are studying the discrete part, the probability distribution is always like associated with the PMF, that is the probability mass function. Now, here mathematically a discrete random variable x having k discrete distinct values will have probability for a particular say for example a point that we have taken out from the sample space, say xi. Now, this thing can be stated as p of x equal to xi, that is what is the probability that our random experiment, that is capital X, is taking up a particular value, and this value may correspond to a event. What is the probability? And we can denote this probability as P of I. Why I denotes the particular event. Now, this the constraint that Pi will have is that since the probability it cannot exceed 1, so it will lie between 0 and 1, absolute value would be 1 of course, and the summation of all the probabilities of all the events, they will sum up to 1. What could be the instances? Blood type of a donor. Why? Because the blood types that we are aware of are say blood type A positive, O positive, negative, AB positive, negative. So, the set is very countable, right? So, since we know what type of blood groups are there, and here the donors are lots in number maybe, though they are countable. So, we can put this type of instance into the discrete category. Then the number of students attending the class, maybe this number would tend to vary from day to day. So, it again becomes a random experiment kind of thing, because we have to wait for the next day during the class timing to see how many students are going to come, and then only we can do the recording part, because 100% attendance is never mandatory. So, it depends which pair of students or what subset of students are going to come to the class the next day. Similarly, we have another example, say total successfully germinating seeds in a farm. In a farm, farmers often they spread seeds in like in bulk quantities, but it's not that all the seeds will germinate. They will there could be some got destroyed due to some reason or other. So, this is again a kind of random experiment that we have to wait for a certain amount of time, for certain process to find out how many exactly seeds are there to germinate. Now, what are the types that helps to model such instances in the discrete space? Binary random variable or binary distributions, then binomial distribution, geometric distribution, Poisson distribution, and there are so many other distributions. These are just the benchmark distributions that we have. So, before we go to the discrete distributions in detail, we also check out what continuous random variables are. So as we have already discussed that what density function is, why density not mass? Because now we are not dealing with a instantaneous value, now we are dealing with an interval of values, and since an interval always is, it comes up with a density of the points that exists in that particular interval. That's why probability mass function, now this word, this terminology gets replaced with probability density function when we speak of continuous random variables and distributions. Now here again very precisely and mathematically we can say that a continuous random variable x with probability for the set of outcomes A, that is the probability is PA, it's denoted by PA, is defined to be the area above A, the region A, and under the curve that denotes by the probability P of x, such that P of x is always greater than equal to 0. Why? Because it's a probability, it cannot be negative, strictly positive it should be, and the total area under this curve has to be equated to 1. The same concept that was there for the sum of all the probabilities for all the events becomes equal to 1 for the discrete case. Here we are only dealing, we are not counting the probabilities, we are not summing up the probabilities, but here what we are doing, we are taking the whole area. Area is what? The sample space of the continuous domain, and we are actually, we do integration of that particular area to find out what the probability, absolute probability will be, and it will tend towards 1, and this curve is known as the density curve. Instances could be the height of a building or the weight of a person, amount of salt in the salt water. We are obviously not going to count the grains of the salt one by one, as also the thing is that it gets dissolved, but there are certain processes through which you can find out the exact measurement. Okay, so we need certain scaling and specialized equipments and all to find out the value that is continuous in nature, to find out these type of continuous domain instances. And some of the types that helps to model these type of continuous models are uniform random variable and distributions, exponential distributions, normal distributions, gamma distribution, and many more. Now starting with discrete probability distributions. Firstly, let's start with a binary random variable distribution. Binary, why binary it is called? Because there are exactly two outcomes. Whenever we have an experiment with exactly two outcomes, that will either tell you that it's a success or it's a failure. Say we denote success with 1 and failure with 0, then such type of experiments are they fall under the category of binary distributions. That is, binary distributions would be more apt to give you an idea of what the results could be. And these type of variables, they come out of experiments whose trials are predominantly, they are known as Bernoulli trials. Okay, the PMF is given by this equation, like if it's a success, the probability is P. If it's a failure, it will be just 1 minus P, or it's given by the symbol Q. Okay, so you can see an example over here. Shortly we will start with the other distributions for them. Thank you.
Well, thank you, ma'am. Thank you so very much for giving us this session. Friends, we are back after a short break and would be discussing more. Till then, keep watching us. Thank you. Hello friends, welcome back to the session. Friends, as you know that today we are talking on random variables and inequalities, and for the discussion on the topic we have with us in our studios Dr. Advitya Sinha. Dr. Advitya Sinha is a professor of computer science, and we believe that you have gathered lots of information through her in the previous session, and this session also we will give you the deep insight into the session. So let's welcome our guest Dr. Advitya Sinha. Hello ma'am, welcome to the lecture once again.
Thank you so much. So welcome back viewers. So we were doing random variables, and particularly we were studying about the binary random variables. Now binary random variables are also called Bernoulli trials, and why they are called binary? Because they have got two values, that is success or failure. Okay. Now let's move to binomial random variables. Now these binomial random variables are very much close to what we have just studied, the binary random variables. Why? Because these binomial variables, they take up the values from experiments which has exactly two outcomes, that is the Bernoulli trials being repeated for many number of times. So we can, in short, we can say that a sequence of independent Bernoulli trials are nothing but the binomial random variables. The PMF, again the probability mass function, because this is a discrete distribution, that's why the PMF of the binomial random variable is given by this formula. What we have done, see that n is our total sample space, and here out of n, if we are we want to take up exactly x values, we want to know that what is the probability that only x out of the total number of say the values that are there in the sample space will occur, then in that case n becomes our total sample space and x becomes the event that we want, we are concerned about, right? P will be the probability of success. So the probability of success is raised to the power the event that we are interested in, and Q the probability of failure. But it could be like chance that those values that we are not expecting also come up during the experiment. So what would be the contribution of those values? We take into a probability of failure, that is 1 minus P given by Q. In an instance, say in a class there are 25 students. If we want to estimate what is the chance that any two students just randomly chosen are likely to have birthday on the same day, right? So how to approach? The best approach is to find out what is the probability that a student will have a birthday on a particularly say any day that we have selected, just random. The student is also selected as random, and any day. So since all the days are equally probable, so we can take the probability as 1 by 365. We are not considering the leap year here. And the probability that that particular student is not going to have a birthday will be nothing, since it's a failure. So 1 minus P, that is 364 by 365. Okay. Now since we want to find out what is the probability that any two students that are randomly chosen from out of the class of n students would have birthday on the same day, there's an event that the common event in which we want at least two students to fall into. So 25 is the total number of students. So 25 C2 is the combination, 25 C2 all the combinations we are taking into account, and the probability of success, that is P raised to the power the number of students that we at least want to have share their birthdays on the same day, and rest goes to the probability of failure. You can see that 23 is a big number, and whenever 1 minus P, that is a failure probability, it's getting exponentiated to a larger value, thereby diminishing its the impact of the failure. So what we get is the result that is being required for finding out the success of that particular event. Next is geometric random variables and distributions. Now here, if we are considering the same independent Bernoulli trials, you can see that Bernoulli trials are so important. We have taken it in binomial random variables also. and here also we are taking it again, but with a constraint that will keep repeating the independent Bernoulli trials till a particular event happens. Maybe a grand success happens, or we might be eagerly waiting for some event and it happens, and as it happens we stop executing that particular experiment. Okay, so this type of phenomena that a particular process is generating, we can model it through geometric distributions. The PMF is given by this Pn equal to 1 minus P. 1 minus P is the same, the probability of failure, that we are waiting for eagerly for an event to happen or for some success to happen, but it has not yet happened for last n minus 1 attempts or n minus 1 timestamps. So this is given by 1 minus P to the power, that is the failure, raised to the power the unsuccessful trials that are being conducted so far, multiplied by only one single success that we are waiting. Once we get the success, we stop executing that particular experiment. So I think this is clear what geometric distribution is and how its PMF is formulated. Now let's take up an instance. Let's assume that there is a communication device that is to receive and transmit packets. So let that this particular device is waiting for the packets to come, and the probability that a packet will successfully come to the receiver or whatever to the communication device is given by 0.75. Okay, it means that 75% of the times the packet that is coming to the system is error free, because you know the wireless through wireless when packets come, say if this communication is a wireless device, the chances of errors would be high. If it's a wired device, chances would be a little less. So whatever the case is, now this communication device is quite reliable because it's having a 0.75 probability of getting the packet successfully received. Now we have to predict the chance that what the device to what extent of time this device is going to wait for time slots. Say we have taken the time slots to be, say 20 time slots we have to wait. Then what is the probability that we are actually, the device is actually waiting for these many time slots to expire before it actually receives the packet successfully. So since we know that we don't need a successful packet to be received again and again, we are only waiting for one successful receipt. So all others, the instance that we were waiting for, all other such copies would be discarded. So 1 minus 0.75 is the failure probability raised to the power those 19 time slots that we were waiting for vain, multiplied by only the single success probability. Next is Poisson random variable. Now Poisson distribution defines the probability Px that a particular event A occurs during time that belongs to a certain interval of domain, and the PMF is given by this formula, a to the power x, then e raised to the power minus a divided by x factorial. Here a is what? A is defined as lambda t. Lambda is the rate of the occurrence of a particular event A. Also a could be, the small a could be called as intensity, as lambda here is the rate and t becomes the time domain, or it could be any other like other domains that might be impacting a particular experiment. Now here you can see that in the figure, when the lambda parameter, the rate parameter is given different values, keeping all other parameters same, you can see that how the curve changes, right? You can see that as the value of lambda increases, that is the rate, as this rate gradually increases, what happens? The peak decreases and the span of that particular curve, the area, it increases, right? So this is one example through which you can understand the impact of lambda, how it is important for finding out Poisson distributions. Taking again a real world example, say there is a queuing system and several number of jobs are entering into the queuing system so that they can reach a particular server for serving their some kind of request or so. Okay. So here what happens, the jobs are arriving to the queuing system, and the rate by which it arrives is 500 jobs per second. So if we want to determine the probability that what would be the chance that 4 jobs arrive all of a sudden, say 4 jobs are arriving during 3 milliseconds. So here what are the parameters that we are given? Lambda is 500, that's the rate. T is given in milliseconds, so we convert it into seconds because seconds is like jobs in otherwise you can do, but since the rate is in seconds, so we have converted to the standard unit. And then how many jobs we are interested? We are interested for 4 jobs in that particular time. Okay, so we're just putting the formula, we're plugging in the values in the formula that we have previously seen here, the PMF of Poisson RV, and this is the value that we come up with, 0.047. Now these were some of the discrete distributions. Now let's move towards the distributions that are belonging to the sample space that support continuous domain values. The first and the very simplest form is the uniform random variable. As the name goes, the PDF of uniform variables, you can see that it's given by the formula 1 by b minus a, where x lies between this interval a and b. Means what? That given this interval a and b, any point chosen from within this interval is equally likely and equally probable to occur. Okay, and whenever you are moving out of this domain, you are not within these values a and b, it means that the density function, the probability that you want will be 0. There is no chance. Say for example, if we consider a robotic movement, a robot has to move, or there are so many robotic equipments these days for even for cleaning rooms also, right? Floors, cleaning of floors. So obviously that robotic equipment is going to move within the 4 walls of the room only. So if we are consider to find out what is the probability that this particular part of the room gets cleaned or something like that, we will take up depending upon what sort of configurations are there to that particular robotic device. All the points, all the areas of that room will be equally probable to be visited by that robotic equipment, right? But if we consider the movement of the robot outside of the 4 walls, it becomes meaningless and the probability becomes 0 in this case. The main usage of this random distribution, of this uniform distribution model is it's used for generating random numbers. You might have heard of random number generators because randomness is perfectly there with the nature, but when we are trying to simulate randomness in our programs through different processes, through different random number generators, what we do, we build kernels, and the kernels that are formed are mostly uniform distribution based. And what else? This type of models, they are they better model the events that equally likely to occur within a specified given interval of time, or it could be a specified space as well. And say we have taken up this example, if we want to find out if x is our random variable and we want to find out what is the probability that x is uniformly distributed over this 0 and 10 interval, and what is the probability that the values we get is always more than 3, it's not less than 3. So what we do, we take up the area of the curve, the values that we get beyond 3. Okay, so if you're going to take up the values like that, what we do, we integrate the curve under that particular region that we want to find out. Next is exponential random variables and distributions. Here, exponential random variable is what we often come across certain experiments that are extensively useful for finding out what type of events are being performed, say between two interarrival times of two other random experiments. Okay, so whenever we are trying to find out the waiting times between such random events, we move towards the exponential distributions. Okay, say it could be the arrival of customers in a queuing system. Okay, so queuing system is a particular say a random experiment, and there are so many acting variables onto it. So arrival of customers given all those random parameters becomes a kind of event that allows us to explain or to analyze what is the waiting time that the customer is likely to spend to get a particular service from that particular queuing system. Also, we can find out the functional lifetime of products with the use of exponential random variables. The PDF of the same is given by the formula that is being displayed. Now we move next to the Gaussian random variable, also known as normal random variable. The distribution depends upon the mean and the variance of a particular variable. Okay, so mean is what? Mean is nothing that the average, and variance is what is the span of that variable on the given space. The density function fx is always symmetric. When we see these graphs also, you can find out that in figure 1 the curve is perfectly symmetric across 0. Okay, so here the mean is, it's needless to say that the mean here is 0, and you can see that as we move towards the peak, the distribution of the data decreases. So at the bottom you can see that 99% of the data you can find at the bottom only. As we move up, this percentage gradually tends to decrease. And in figure 2 you can see that if we keep changing the say the standard deviation, the span that particular distribution is covering becomes lessen, and the peak increases likewise. So these are the parameters, basically the mean and variance, through which you can control the event space or the event space of particular randomly generated events, so that the outcomes of a particular random experiment could be followed. Next is gamma random variable. Here the PDF is given by this equation, where you can see that there is gamma with a parameter alpha. So gamma alpha is the gamma function. It's a very famous function, and through induction, if we carry out induction process, you can see that gamma number is n, then it could be approximated to n minus 1 factorial. Now these were all the distributions that we came across, the variables, the phenomena, etc. Now what happens if we want to find out an expectancy measure of the values that the particular distribution is being generating? Okay, so expectancy measure, how do we define it? Suppose we have a random variable x that are taking up finite number of values. Okay, we have taken a discrete domain here into consideration to understand how expectancy measure is being calculated. Okay, the same expectancy measure is there for continuous domain also. As of now, let our random variable x is a discrete random variable, and it has probabilities associated with it, because say for example, if we take up an example of coin tossing, head and tail, so we'll always have a probability associated with how many, what is the probability that we get a head, what is the probability that we get a tail, like that. So the number of events we have, the same number of probabilities would be associated with that, with those events. Now the expectation of x in that case will be given by the product of the value and the associated probability. When you sum up all these for all the events that are there in the available space, then you come up with the average value, and this particular average is basically a weighted average, a weighted mean of all the sample space that are producing outcomes. And these are very useful, no doubt, when the corresponding experiments are being conducted for larger number of times and you are getting outcomes that may tend to vary instantaneously but might show some kind of prediction in the long run. Say if we take up an example of a game in which a fair dice is being rolled. Okay. If a double is being rolled, the player would win $5, and if an odd number is rolled, he wins $2, and in other cases he will lose $5. Okay, so the player is having two fair dice and he is rolling, and it will depend upon what the values are there on the faces of both the dice. He'll get a certain kind of winning. So the question here is to estimate what the expected winnings could be for that player, and on average, if this game is being played for a large number of time, for a longer period of time, then what is the expected amount that the player is going to accumulate? So how do we approach? We first find out that what's the probability being associated with rolling a double. Okay. So if you are rolling a double, how many doubles would be there? It could be situations like you are getting 1 on a particular dice, say dice A, and on dice B also you got 1. Okay, so 1 1 would be one pair, 2 2, 3 3, 4 4, 5 5, and 6 6. So there are 6 such doubles, right? So 6 by 36 we end up with probability 1 by 6. Similarly, how many odd pairs are there? There are 18 pairs. So 18 by 36. 36 is what? 36 is the exhaustive sample space. Okay, and 18 is the event that we are concerned about. So 1 by 2 becomes the probability of rolling a odd number. And we are concerned also about what if we are not rolling either a odd or a double. So what we do, the best way is you add up the probabilities of a double and an odd and subtract it from the absolute value 1, because we know that probabilities will not exceed 1. So 1 minus whatever event we are dealing with will give you 1 by 3. That is the possible value for the probable value for getting neither a double nor a odd. Now we are in a position to formulate a table, the expectancy table, that will help us to analyze the winnings for this player X. Okay, so we know the values that if a double is being rolled, we'll get maximum, that is $5. So the value is 5, and the probability, associated probability with that amount is 1 by 6. Similarly, for $2, it's half, and minus $5, that is the player has to return $5, that's why negated, is 1 by 3. Okay, so now to find out the expectation, what we do, we have just multiplied the value and the probability and summed up over all the possible events that were there. Okay, so here we had 3 events: rolling a double, rolling an odd, and rolling neither a odd nor a double. Okay, so we have just summed it up, and the expectation is 1 by 6. So 1 by 6, if you multiply it with 100, it comes out to be 0.166, that is 17 cents. Okay. Now the inequalities. Now when we come across probabilities for finding out the randomness in the certain phenomena, for finding out obviously the performance of a certain system, we also need to perform some sort of approximations during the derivations that we would do. Say for example, we are deriving some the waiting time or the inter-arrival times in a queuing system or so. We would need these type of inequalities to make our work a lot more easier, right? So here we have Boole's inequality. What it says is the arbitrary, if we have a list of arbitrary events, not necessarily independent of each other, then the probability of the union of all these events are not more than the sum of their individual probabilities. Okay, so if we are individually summing it up and you are doing a union of all the events, now this probability will be always less than the sum of the individual probabilities. That is, the sum of the individual probabilities are acting as a upper bound to the probabilities of the union of events. Okay, this is also called Bonferroni's inequality. Binomial inequalities, there are so many binomial inequalities, so you can go through all these inequalities. That helps us to perform approximation in different stages of derivations. And then we have Markov inequality that says that if y is a random variable assuming non-negative values, then if we have somewhere, we have to find out probability that a particular random variable y is greater than or equal to some value, some positive value t, then we can always replace this part by expectation of that particular random variable divided by the time domain, or whichever domain would t refer to. Okay, and obviously since we are strictly referring to the non-negative values, it means that Markov inequality is providing you a weak bound, and this weak bound could be extended to give better bounds using Chebyshev inequality that is shown in this equation. So all these inequalities will be studied into depth in the next lecture.
With this note, thank you, ma'am. Thank you so very much for giving us this session. Friends, you are requested to write us at info.cec@nic.in. This is the ID where you can post your questions as well as you can give your feedback. We are going to meet again very soon. Till then, take care. Goodbye. Thank you, ma'am. Thank you so very much.
Thank you so much.